In this video, we will change the order of integration in a triple integral. So we're given this integral with certain bounds, and the order is zyx for the iterated integrals. And we're given 4 different orders to change the order of integration of the same integral. So before we start, it's probably worthwhile to draw the region that's described by the original integral. That way, when we have the picture, it'll make the rest of it easier. So let's look. The first integral here, the z integral, goes from 0 to 1 minus y. So that means that the bottom of this region is just z equals 0, the xy plane, and the top is the plane z equals 1 minus y. So whatever it looks like, the bottom is the xy plane and the top is the plane 1 minus y equals z. Next we look at the outer 2 integrals. So these integrals, they describe the shadow of the region. If we were to look down at the region from above in the z direction, this is the shape we'd see, what's described by these 2 outer integrals. So it goes from minus 1 to 1 in the x direction, and in the y direction, the bottom is the curve y equals x squared, and the top is the horizontal line y equals 1. So if you put all this together and try to draw it, what you'll come up with is this. So first let's draw the shadow that we discussed. If we look down from above, we'll see something that goes from minus 1 to 1 in the x direction. And in the y direction, the bottom is the parabola y equals x squared, and the top is the horizontal line y equals 1. So we'll see something like this. So here's the parabola y equals x squared. Oops. So this is the shadow that we'll see, is this chunk of the parabola. So this is going to be the bottom of our region. And remember, the top is the plane 1 minus y equals z. So it's going to look something like this. And it's the region inside here. So in other words, one way to describe it is it's a wedge that's cut out from the cylinder y equals x squared, cut out by the plane z equals 1 minus y. So this is what the region looks like. Now let's try to change the order of integration in these different ways. So first, part A, we have dy, dz, dx. So since the first, or the inner part, is dy, that means that we have to look at it from the y direction, meaning imagine your eye is over here and you're looking this way. So we have to say, what's the top and the bottom? Or maybe more accurately, what's the front and the back if we look at it from this direction? Well, the front, or the top, is again the plane z equals 1 minus y. And the back, or the bottom, is the part of the cylinder y equals x squared. So again, the top, which I'm shading in red, or the front, is the plane z equals 1 minus y. But we want to write it in terms of y, so that's the same thing as y equals 1 minus z. In the back, which I'm drawing in blue, is a part of the cylinder y equals x squared. which is already solved for y. So, in part A, the first integral, or the inner integral, in terms of y, goes from x squared to 1 minus z. Because those are the descriptions of the surfaces which are the front and the back if we look from the y direction. And now, just as before for the original one, the outer two integrals should describe the shadow of the region if we project it, in this case, onto the xz plane. So we need to think what that looks like. So again, if you think of looking at the picture from the arrow that I drew, and imagine you have no depth perception, and all you see is the flat shadow of the region in the xz plane. Let's think about what it is. Well, the boundary of it will be this sort of parabola that I'm going to color green. So we'll have no depth perception, so it won't look slanted, it will just look flat. We have to think of what this will look like if we project it. Well, if you think about what it is, it's the intersection of the cylinder and the plane. So if we set them equal to each other, you get x squared equals 1 minus z, or z equals 1 minus x squared. So in other words, if we project onto the xz plane, this is what we'll see. We'll see the parabola z equals 1 minus x squared, and it will be filled in. So this shading I'm doing is the red face in the picture above. So we need to describe that with the outer two integrals. And we have to do it in the order that we're told. So the middle one needs to be z, and the outermost one should be x. So x goes from minus 1 to 1, and z goes from 0 up to 1 minus x squared. Okay, so that's part A. Now, just to save space, I'm going to erase some of this and redraw the picture. So let's draw it again. So here's our region. Let's try to do part B. Again, y is the first integral, so the inner integral will be the same. We'll go from x to 1 minus z, for exactly the same reason as before. Oh, I didn't finish writing it up here. So the front and back are the same as in the previous one. The only difference in part B now is, again, we're looking at this picture in the xz plane. We're just describing it in the other order. So now z is the outermost integral. So we need to say z is between a constant and another constant. And of course it's going to be between 0 and 1. And now remember, this curve here is z equals 1 minus x squared. So if we solve that for x, that's the same thing as saying x is plus or minus the square root of 1 minus z. Plus or minus because we have to take the square root. So the minus will be the left side and the plus will be the right side of the parabola. And so those are our bounds for x. It goes from minus the square root of 1 minus z to positive square root of 1 minus z. Okay, that's part B. Now part C. So now x is the first. So now we have to imagine looking at it from this direction, sort of how we're looking at it in the actual picture that we drew. And we have to think, what's the front and back? So if you think about it, the front and back that we will see, if we look at it from the side like this, will be the edges of the cylinder y equals x squared. So here, the front and the back are going to be the cylinder. But we want it solved for x, because the first integral is x. So this is the same thing as x equals plus or minus square root of y. And so the inner integral for x will go from minus square root of y to square root of y. And again, as always, the outer two integrals now need to describe the projection, or the shadow, of the region if we project it in the direction we're looking. In this case, that means we need to project what we see onto the YZ plane. In other words, pretend you're looking from the arrow that we drew, and that you have no depth perception, and you just see a flat picture. What will we see? Well, if you don't have any perspective and you just see something flat, you're just going to see this triangle, which goes one in the x direction and one in the y direction. Or sorry, one in the y and one in the z. And if we're doing it in this order, y is on the outside, so the y bounds should be constant. It goes from 0 to 1. And then z goes from 0 to this line, which is the line z equals 1 minus y. So the bounds are 0 and 1 minus y. Okay. Last one is part D. In part D, again, x is the innermost integral, so this will be the same as in the last one. We're again looking at it from this direction. But the last two are flipped, so we have dy, dz. So again, we're describing the same triangle as before, but in the other order now. Now z is the outer one, so we need the z bounds to be constant. So z goes from 0 to 1, and y goes from 0 up to, again, this line, which was the line z is 1 minus y, but we have to solve it for y now. And if you do, that's y equals 1 minus z.